Hi everyone, thank you guys for coming to Q-munity's workshop. So today we have Sara Charmchi presenting to us on how to become a quantum developer. And maybe a little bit about Q-munity. A Q-munity is a student-run organization dedicated to educating.
نمیدونم چیه اصلا.
Let me see. Okay. All right, let me continue that. So Q-munity is a nonprofit organization dedicated to educating everyone and anyone on quantum computing. So today we have Charmchi today presenting on become a quantum developer. And just keep in mind, make sure you guys are muted just in case anything happens during the presentation. We wouldn't want to interrupt her amazing talk. Sarah, how about you introduce yourself and maybe get started with your presentation?
Yes, can I start it? Yes.
No, of course. Go ahead. Love to hear what you have to say.
Okay, hi everyone. I'm very excited to be here today. I will give a talk on how to become a quantum developer. My name is Sara Charmchi, a master's graduate in physics, mainly focused on quantum computing. I've defended my master's thesis in 2019, and I worked as a developer and data analyst for a while. And later I got interested in software part of the quantum world. I worked on designing and simulating quantum circuits. And currently my main focus is on my tech startup, and I'm still learning. Oh, okay, I will start it. Everyone, it's okay? Okay. The subject matter of quantum computing is in general very advanced, complex, and confusing, and even some complicated. I'm not an expert person. I'm not an expert person to simplify the subject for you, as there are people far more qualified than me to talk on the theories and physics side of the things. In this talk, I won't get deep through the quantum physics. I prefer to share my thoughts and ideas on quantum computing, as well as some experiences on programming. So that would be, I think that would be a friendly conversation. First of all, I will give you a brief introduction to quantum computing and its differences and applications compared to classical computing. And then we'll discuss what quantum computers are about and explore some famous frameworks to figure out who is a quantum developer. And in the end, we are going to look at how to run some non-trivial programs on an actual quantum computer, which I name it as sense of inspiration. All right, why should we move to quantum computing? As we know, we use computations because we expect some characteristics from them. And these characteristics depend on the base element we choose to build our computational system on. If we take a look at computer generations, we can see this evolution of these base elements. For some reasons, engineers try to make these base elements as small as possible, from vacuum tubes to transistors or even smaller transistor and integrated circuits. Why is that? Why we try to make these base elements as small as possible? First of all, it's because of three reasons, I mean. First of all, with smaller elements, we can pack them all in the same volume. So we have a bigger number of elements, bigger number of states in the same volume. Second, the smaller elements have a smaller inertia in electronic devices. This inertia is called inductance. And the smaller conductor, the smaller inductance it has, and so it can change the states faster. So we can compute faster. Again, with smaller conductances, smaller inductances, we can dissipate less energy, and which is an important issue. So now, computer devices reach this limit. I mean, the nanometer-based elements. I mean, p-n junction, that are only 200 times bigger than a hydrogen atom. This means that this miniature organization has a limit. We can't implement a p-n junction on an atom or a molecular. So we have to choose something else if we want to grow our computational power. So this something else has to be as small as an atom or even smaller, but at least scales, I mean an atom scales. we can't disregard quantum effects, which means that the new generation of computers must employ the quantum effects. So it appears that the new generation of computers is no way but to be quantum. I mentioned the base elements, which are bits in classical computing and qubits in quantum computing. I assume that most of you are familiar with bits and its characteristics, but I want to compare both of them at one glance. Now, a bit is a transistor that registers a high voltage or low voltage either, which corresponds to 1 or 0 respectively. But qubit is fundamentally different. A qubit is a two-state quantum device and uses quantum effects, which means that it can represent 0 and 1 as a result of special properties of quantum effects. I mean, superposition and entanglements. For instance, we can use spin up and spin down an electron as qubits. Power increases exponentially in proportion of number of qubits. However, in bits, power increases in one-way relationship with a number of transistors. This is why quantum computers can help us with heavy optimization type of tasks or tasks that have many possibilities. And yet, quantum computers have high error rates and need to be kept ultra-cooled. However, classical computers have lower rates and can operate at room temperature. We can use quantum computers for special tasks like simulations and optimization problems, although most everyday processing is best handled by classical computers. Let me interpret it for you with somehow famous example. I told you quantum computers very well for problems that exponentially explode. Problems like logistics, such as the most ideal delivery route for trucks, or even concepts like planning for companies. Each choice branches out to so many possible choices or opportunities. Let's consider we're planning strategical events and you're attempting to sit people together in your desired mood. If you have just one table and 5 seats, how many combinations do you have? It's about 5 factorials, 5 multiplied to 4, to 3, to 2, and to 1, which is about 120. 1 table, 5 seat, and 120 possible combinations. What happens if you add just one table, one seat, which is 6 factorials or 720? What about 10 seats? It's more than 3 million combinations, possible combinations. That's what happened to chemistry simulation. You currently can rely on classical computer to do chemistry simulation reliably. What about quantum computers? Theoretically, yes, they can. What about the real life? We hope so. We are working on that. But how do we get from the idea of qubits to real quantum computers? It's a challenge. I'll describe the one that we'll use later. I mean, IBM quantum computer. Different products may have different structures and methods. We'll focus on IBM quantum computer. As you may know, a qubit consists of two energy levels, which are denoted as 0 ket and 1 ket. Then we have a nice tool to represent this state, which is block-sphere. We can say that it's a geometrical representation of a state space of qubits. So then how do this energy level and block-sphere occur in the cloud? And you can use it at the cloud service of quantum computer. I want you to have a big picture what's happening. Let's continue step by step. You have a laptop which you can log in and connect and send some information to the fridge, but it's not a normal fridge. It's expensive and special fridge. Inside the fridge is a chandelier. They call it a gold chandelier because it's made of gold, full of wires and cables. It's a superconducting dilution fridge. The point here is that everything that we expect to be quantum sits at the very bottom. At the very bottom of this chandelier is a superconducting qubit chip. What you see here is a device with several qubits and several readouts that all sit at the surface of the chip, which can be silicon or other dielectrics. If you focus on the qubit side, which is type of resonator, there's a structure with 2 metallic pads that's connected with some sort of inductor. You can figure out the relationship between these resonators and the picture of the block sphere. I don't want to go deep into details, but there are microwave oscillators or electromagnetic oscillators, or oscillations of electromagnetic field, which we can represent using circuits. That allows you, in other words, support electromagnetic circuits with electromagnetic fields, which themselves allow you to create a type of block sphere and then control it, manipulate it, or so forth. And they allow you to measure so that information can flow back from the Hilbert space all the way through the circuit, to the fridge, and to the laptop, and back to, and this closes the feedback loop. Now, it's somehow clear what quantum computer is about for you. However, I want to recall some important points. There is no real qubit. There is no such a thing that real qubit in life. They are just two-level approximations. We can usually take two levels of much larger system and name them as qubits. All of them come from nature, quantum nature, and nature of the atom, and its quantized energy levels. And this nature is really special. The atom must isolate it from environment and thermal bath, so the noises want to destroy the quantum properties of the atom. And because of these properties, and to have much more control over the qubits, we use artificial atoms. The artificial atoms are created by electromagnetic circuits. This is why IBM has moved to superconducting world. Currently, you may have a big picture of what's quantum computers, but you may think that how is this useful? How can I make money out of this? Or will it get job? Well, in my opinion, the answer is based on time. If you get the answer today, it's just for today, not for 10 years later. Quantum computing has a little community. However, there is much more advertising than reality. You should decide logically. The path to working for quantum computing, this is still narrow if you consider all over the world, not just a few famous companies like IBM or Microsoft. You need to keep your feet down on the earth and explore things that are useful in day-to-day work. So you should look in web development, machine learning, or data analysis if you want to make much more money. This has happened to classical computers in 70s or 70s or 50s, I think. There were just some pioneers. In my opinion, my point of view, quantum computing right now is for the curious and passionate, for the pioneers who plan to change the world. So if you want to continue without any thought about the possibility of the profit, welcome to quantum computing world. As I promised, we're going to explore some useful tools for quantum computing. I'm going to go through 3 of them. I want to put more focus on the last one, as we are going to experience coding with an actual quantum computer. But before that, I want to recall the process. Circuit model. The most popular model of quantum computing is circuit model, which described operations on qubits as a sequence of gates that can be represented as matrix being multiplied by a vector. In order to build circuits, you should introduce qubits, or in better words, you should initialize qubits and bits. In some frameworks, like Qiskit, you should create registers. Quantum and classical registers in Qiskit should be thought of as channels of information for bits and qubits. Then you want to implement some operations to manipulate quantum bits. We use quantum gates. As you're familiar with logical gates in classical computing, we have also gates for quantum computing. They map the existing state of a qubit to another state. We have different gates like Pauli gates, CNOT gates, or Hadamard gates, or many others. For example, Hadamard gates can flip the state to superposition state. And in the end, we have measurement, the special operation, an irreversible operation that determines the final values of qubits. It's just like opening the box and showing your CAD experiment. After that, you can visualize your circuit or simulate it in the simulator, or even run it in an actual real quantum computer, or whatever you want. Remember that it's just the basic. Okay, I want to start with Quirk. I think most of you might have never heard of this, as it's not a commercial product. Quirk exists because someone just got interested in quantum computing. It's that much interesting. It is drag and drop quantum simulator that runs in your web browser. It's continuously resimulate as you edit the circuit, providing immediate feedback. It's very good at small scale iterative experimentation. In my opinion, I found it as one of the best for learning quantum computing because it's incredibly fast with no sign-up process, like Microsoft or Qiskit. Quirk has no evaluate the circuit, or you cannot, it's always evaluating the circuit. It's part of their code. You don't have to think about getting results. It just happens. Just like you experiment freely, and immediate feedback from the experimentation give you a feel for how adding or moving a gate will affect the output. And also they have some tutorial videos on YouTube channels, and the sources are also available in the GitHub. Building circuits is really simple in the Quirk. You can save the circuit in your bookmark or browser, add gates, drag and drop between gates. For example, in this GIF, you can see that each horizontal line is a qubit, or even you can implement gates, for example, heteromorph gates, and you can see that the percentage of the choices chances varies, which shows the superposition. Also, the blogosphere is a very interesting visualization of qubit state. It also has some famous examples, such as Kruger's search algorithm, quantum teleportation, and many other useful examples. You can find them on their GitHub page. Okay, let's move to some commercial products from Microsoft. Experimentations like drag and drop and changing circuits and simulators with full knowledge of quantum state is a great way to learn the tools. But to really program a quantum computer, you need to follow quantum rules that observing the quantum state can destroy it. That's where Microsoft's QSharp programming language comes in. If you're a computer person, I think you would get used to it really easy. QSharp, they made something that's really similar to machine language. You have two ways to use it. You can write your quantum codes with QSharp, or you can use familiar host languages interface like Python to call QSharp code. This can more visualized as what we do in our classical computers. We write code for GPU separately, and then we use the code written for CPU to run and access the results from the GPU computation. So for the comparison, I think you can QSharp code is like GPU code, and Python or C# wrapper code is like CPU code. All this can happen locally in your computer. However, if you want to run a QSharp program on quantum hardware, real quantum computer with Azure Microsoft product, you must sign up in the website, and the process is really easy. For example, in this GIF, I bring one of the Microsoft tutorials for teaching quantum computing with QSharp. They use Python to implement the classical side of an algorithm and call QSharp to run the quantum side, all in a single code environment in a browser. The course is recommended for students. However, in my point of view, it's much more than that. It's not just for learning. As they announced, it is a high-level programming language that allows you to focus your programming at the algorithm level. So I think it's better for the developers. And the final one, Qiskit, or it's better to say IBM solution for quantum computing, because it's a very good package of the whole process of doing quantum computing. First of all is the Qiskit, which is an open source Python module for building quantum circuits and simulating operations on qubits, and stuff like Qiskit Terra or Core or Metal. For example, they have different purposes. I won't go into details. They've also provided an open source online textbook and professional YouTube tutorials. It doesn't mean that the other companies like Microsoft or others didn't provide these sources. I recommend this one because I myself, after trying most of these products, find this one more useful and clear. There's also a community of people that help each other on Discord channels and Slack and so many other things that make the learning process easier. In addition to our IBM Quantum Composer and IBM Quantum Lab, where you can build, edit, and simulate quantum circuits. And in the end, you can run your program on the IBM quantum computers, processors, I mean the real ones. In this GIF, I want just to show you, to give a picture of what is happening while using IBM Q-Circuit Composer, just for example, their online service. Okay, it's enough, I think. Let's do some coding using Qiskit. You need Python, Jupyter Notebook, which is one of the best for writing code, and also Qiskit libraries. After that, we need to import some packages that the process begins. You need to define or initialize your qubits, and because you're programming on a classical computer, you need bits as well. We want to implement some operations on our bits, and we use on our qubits. We use quantum gates to recall when using, for example, Hadamard gate on our state. It flipped to the superposition. And at the end, the measurement function is the observer and takes the collapsed qubits value and puts them together as the final out bits. Then it's time to run. You can visualize your qubits in any desired method and then run it on the simulator or on an actual quantum computer. It's actually an interesting experience, I think, to know that you're writing code that's not running on your processor, but actually on real quantum computer. But before that, I want to be sure that you're familiar with quantum gates. So I pick a GIF, which is designed by a quantum computing student, as I'm not mistaken, Sara. I really want to thank her. Really beautiful design. It's very clear to understand the gates. As you can see, I bring a few famous gates. It's always that we have so many other gates. First is the identity gate that does nothing to our state. Then we have a controlled NOT gate, a gate that operates on 2 qubits. This gate is a conditional gate that performs an X gate. On the second qubit, we call it the target qubit. If and only if the state of the first qubit, we call it control qubit, is 1. And then we have a Pauli gates, X, Y, and Z. Then flip the state of the qubit, as you can see. So let's try it. First, head to IBM website and create an account. Then choose My Account, and then you will see an area, your API token. If you don't have one, go ahead and generate one for yourself. You should copy your token, but in my opinion, it's better to save it somewhere on your PC. Okay, back to Jupyter Notebook. It's time to introduce yourself to IBM and get access to the processors. This saves on your actual machine, so you need to do this just once. With running the last code, you will have a list of IBM machines. You might see other available machines based on your location. So don't worry if you don't see mine. Choose the one that you like, or for this task, because we are just testing, you can choose the faster one, or the one that, for example, IBM Blend, which is I have 12 cute. Next up, let's connect to a quantum computer using the following lines of code. I don't want to go into details. I want to explain each line of the code to make you bored. I want to just focus on the outputs. Let's consider the left histogram. Recall the control NOT gate will flip the target qubit, the second one, if the control qubit, the first one is 1. The second qubit was 0, since it was never turned on, and the first qubit, qubit 0, was in superposition. Superposition, I mean the qubit is in any possible states, but will collapse on a single state when observed. So the answer would 0, 0, and 1, 1. But why we have all of them, all of the different probabilities? This is noise. Expect noise and rely on probability. This is why we make many observations so that we can see the actual distribution of outcomes. Thus, we see close to 50-50 split between 0, 0, and 1, 1 with this circuit. There's obviously noise too, but in an ideal quantum computer, would only see 0, 0, and 1, 1. Then let's consider the right histogram. Notice we didn't get a perfect 50-50, but there's no 0, 1, and 1, 0. Why is that? The simulator simulates a perfect quantum machine. Maybe one day we could have one real perfect one. I want you just to notice differences between simulators and actual machines. It's always amazing to run your code on actual processors, but no one would recommend this. But first of all, it would waste your time waiting queues, and second, you would waste others' time in queues, and you're not running your code for serious purposes or goals. Okay. When you get familiar with the concept of quantum information and quantum computing, and later become professional at programming, you may prefer to make a portfolio for yourself. Let's explore some ideas. I will tell you the ones that I have done in my own career path, and I myself take these suggestions from people far more qualified than me. First of all, try to get qualified in linear algebra and physics side. I would recommend build a quantum random number generator, implement Gruber's search algorithm, use Shor's algorithm to factor a number, tackle noise with error correction, or even sort images using quantum machine learning algorithm. And the list just goes on, and you can find more of these suggestions in Qiskit blog community. They have collected many of these. And the second step, you're familiar with most of the fields in quantum computing in this step. Now it's time to choose your priority. Most of the expert ones in this step recommend making games. It's fun and full of challenges. Don't think of something big or incredible, just try something useful. It's a way to run your program with the knowledge turn the knowledge about quantum gates into something creative. It's one of my biggest regrets because I didn't do that when I was master's student. But in the end, you're ready to do something serious. I mean, you can contribute to research projects or open source projects. If you choose research, there are a bunch of mentorship programs or university programs out there that can help you enter the academic world and do scientific researches related to your background, including optimization tasks and designing algorithms, etc. But if you choose open source projects, which I think that would be better for a career path, open source projects often attract a community of users and developers to help with testing, bug fixing, and eventually maintaining the projects. You can try writing new backends for Qiskit, designing your own gates and Qiskit pods, and eventually think of high-level application for chemistry or material design. I would recommend QOSF or Quantum Open Source Foundation. It's not advertising, but just I really recommend that. They collect a list of available open source projects, and they have also monthly challenges on their website. All right, finally, I want to conclude with a quantum overview. In previous slides, where I was talking about the future and the jobs, I emphasized passion and curiosity. Now I want to tell you, if you're passionate enough, there are enough opportunities. These years, in my opinion, a transition from quantum science to quantum technology. You shouldn't take this, we have now entered an engineering phase, nor does this mean that there is no science left to do rather. There are now many reasonably defined parts of the system that need a rigorous focus to come together. This broadening of entry paths into quantum computing really opens the door for lots of opportunities to contribute to the future of quantum computing from a family of researchers, engineers, developers, designers, and even builders. In the end, I want to tell you that I think you're the lucky ones. You can see the enthusiasm of our growing community, and I think the future of this technology is really bright. Thanks for your attendance, and thanks, Sarah. I really appreciate your invitation. Thank you.
Wow, that's very detailed and very amazing. Thank you so much, Sarah, for the presentation. It was amazing. So right now, until the end of until like 1 p.m. EST, we're opening the floor to any questions. Feel free to unmute yourself or send any questions in the chat, and Sarah can answer them all for you. So I guess I do have some of my own questions. I think it's really interesting how you explained getting into quantum computing through like different resources and different like mindsets. And I was thinking about how quantum computing is very different from classical computing, and how exactly do you think someone should approach it in a way so that they can succeed in the field, since it's so different from what a lot of people are usually used to? So like, what are thinking concepts that you think people should really focus on as they approach different quantum algorithms, or any problems they might want to solve using quantum computing?
Spicy question. I think, in my opinion, we have a diversity of people in this field, from computer science, physics, maths, and even finance. So I think different people have different mindsets. So you can't just recommend something that they should obey. For example, I myself, I got my physics degree, and I have a physics point of view. So I can't, in my opinion, for example, the developers that they have a computer science background, they don't. It's not necessary for them to get deep into physics. Because you can just do programming and just know some math and physics to do and develop right algorithm. But when you want to do research and physics side of the thing, for example, in IBM, their R&D, they should know physics. So most of the people have PhD in physics. But as I told you, because these days, we have quantum technology, not just quantum physics like 100 years ago. We have different backgrounds. For example, I see people from finance that they have a finance degree and they don't know really much more physics, but they do really interesting things in machine learning. So I think people should find the border that connect their background to the quantum computing. That's all I think.
Oh, that's amazing. Yeah, I've noticed a lot of people going into like finance and quantum computing and AI and quantum computing, and I found that really fascinating. So in the chat, I see a question from Rodrigo, and he asked, what's one book you would recommend to get started on quantum computing?
I really love this book, but I think most of you may read this book. Quantum computation, and quantum information. I think Michael Nielsen. Most of the physics and mathematics and quantum information students have read this.
Ooh, okay, that's amazing. Do you know how to spell Michael Nielsen so that people can have an easier time finding the book specifically?
I think it's N-I. Wait a minute. It's Nielson.
Okay, someone sent it in the chat. It's Nielsen. Okay, thank you, Rodrigo, for the message. So we have another question from Kevin, and he asks, how will quantum and classic computing work together?
It's a good question. For example, in my startup that we are working on, we really work on the border with quantum computing and classical computing, because, for example, in data science, as we are working on the oil and gas industry and connecting the oil and gas industry to data analytics and data analysis, we have heavy optimization types of tasks and tasks that have many possibilities and choices. And in this modeling, in this simulating, we use classical computing. But when it's more heavy and more complicated, we need quantum computing. And we're working on that to do a heavy optimization type of tasks. For example, here, at this time, many famous companies are working on this because right now quantum computing didn't reach to the quantum advantage. So you can't deny the classical computing. You should work them together, and when you can do more of classical computing, you can reach to quantum computing, as if you can and you access to the quantum computers. I think that would give you the answer.
Thank you so much. That sounds great. We have a question from a high schooler, and they are interested in a career in quantum computing. They ask, what would you suggest that they do as a high schooler?
Thanks for your interest. At high school age, I think it's better to focus on fundamentals. I'm not an expert person to recommend something for you, but if I was at your age, I would focus on fundamentals and physics and mathematics. You may have access to programming and gates and quantum information theories, but I think it's not necessary. If you focus on mathematics and physics and be professional at this, when you get to university, you're qualified enough to get to quantum computing. It's better for your career path, I think.
Sounds amazing. Thank you so much for the amazing advice. So we have a question about, is there any threshold below which the errors in a quantum computer cannot be undone? If so, then algorithms will have to run several times. Would they still outperform classical computers?
I can't hear you. Can you please repeat?
Oh, okay. So there's a question. Is there any threshold below which the errors in a quantum computer cannot be undone? If so, then the algorithms would still have to be run several times. Would they still outperform classical computers?
If you want to know the error correction and the encrypted something like that, I prefer not to answer this because I'm not the expert person in cryptography.
Okay. So we have another question from Rodrigo. He says, nowadays, do you think the best application for quantum computing could be solving NP problems?
NP, or you mean NLP, neural network?
Um,
NLP?
Well, they typed NP, but I'm assuming it's probably
It's
NLP.
NLP, I think.
Yeah.
I'm not really familiar with NLP and neural network, but if you want to, did you say something?
Oh yeah, they clarified it's non-polynomial.
Yeah, I think they want to know that what applications they've done for this. Yeah, I mean, in chemistry simulations, they've done many things, but I'm not a very expert person to answer your question. I'm sorry.
Okay, sounds great. So Mahabulbul from Penn State asked if you could share a bit about your current works and your startup.
Yeah, we are working. Thanks for your interest. We're working on a platform, software platform that connects data science to oil and gas industry, and we're working on a system on a detection and multi-detection and optimization system. We have a team for different fields and backgrounds from data analysis, data mining, engineering, software engineering, business management, and as we're working on optimizations tasks, we'll try to connect the classical computing to quantum computing for our heavy optimization types of tasks. And we're now at working at our MVP, and it's our plan to make the startups.
Sounds amazing. That's really interesting what you're working on. So, are there any other questions? Feel free to unmute yourself. We'd be happy to hear from you as well, like if you'd like to ask any questions. So maybe I'd like to hear a bit more in depth about like your experience so far with starting a quantum computing like startup. What is it? What do you usually do when it comes to like building your own like startup, and the procedures and what to prepare for in terms of like building something this unique?
Yes, it was. I was working in my master's graduate, in my thesis, I was working on a theoretical part of quantum computing, and somehow it makes me bored. After that, I think that I should make something real, not theoretical. So we collect a team, different backgrounds and different fields and passion. First of all, we want to get to the oil and gas industry because they sorry, I think something happened. Can you hear me?
Yeah, you lagged a bit, but it's better now. I can hear you now.
Okay. Yes, well, we collect a team of different people, and I don't think we have a startup that some days ago, and we just failed, and we did something for about 6 months ago. We started something that's more useful the industry, and worked on it about 6 months, and now we get in a competition, and we were just the first place at that competition, and we just with that competition everything starts at that point, and we're working on our MVP, as I told you, and business plan. different people have different perspectives, and because of our different perspectives, we really reach to something useful and something incredible. I think before that, we were just physics students that come together and try something like software engineering and software platforms. But at this point, we try to make this more industrial, and they just I think the passion is most important thing that people with different minds collect together and make something creative and incredible.
That sounds great. Yeah, it's amazing that you have decided to actually build something with what you know and actually help and make an impact. So this is amazing. Thank you so much, Sarah, for your contribution to the quantum computing industry. So how about I'm not seeing any questions in the chat, but if anyone wants to unmute yourself, that'd be really helpful. Other than that, I do have like a few more questions. So I guess I'm interested in mainly like how you kind of like what's the process of actually starting like a startup in a way, and maybe talk a bit more about like your difference between like theoretical works and actually applying it, like what's something you didn't really expect, because like I understand works in theory may not always be something that happens, may not always be the same when you actually apply it in real life. So is there anything you found that was quite unexpected when you actually start working on it in real, like through application?
Yeah, when you start your, for example, thesis in the university, you think that everything that you like that could happen, and everything that you want, just you can start and go ahead. But in the industry, you can do just anything that you want. You just focus on the things that the industry and people and the market really wants. When I got from the theoretical part to the real industry and workspace, I see that most people and supervisors really make you something like you not real, you think that you are the expert one at university, and when you go to workspace, so see that something is everything is really different. You should gain many skills, but if you are at university, you think that you know everything because just read books. But market and industry is not books, it's people and what they need. As I get to startup space, I find out that the most thing that I really didn't like, for example, oil and gas industry was really I'm not interested in right now even. But it's useful, and you can implement your knowledge to something creative and useful. So we collect people from different backgrounds, and they were just employers, but we try to make something different, even if we don't like the field, even we don't know the field. We try to collect knowledge, gain skills, see different people, and go to different places for mentorship programs. And even at my age, we try to enroll some competition that before that we think that it's too late for us. We are 26 or even more, and it's really too late. But when you get to the workspace, too late is not really, it's not meaningful. You just try to start. And passion, I think.
Yeah, that's a really good answer. Yeah, it's very, I found that through speaking to a lot of people, they always say that working with people is always the biggest jump between what you learn in school and what happens in real life, no matter like what industry you're working in. So I found that really interesting. You talked about like thinking like the jump between like university and real life. It's really fascinating because as a high school student, I haven't really been exposed to much real life experiences yet. So this is really great advice, and I think this applies to a lot of things, not just like the quantum industry. And I find it really interesting. Yeah. What I found interesting is that quantum computing isn't really something like people day-to-day use it in like their day-to-day life. So I was just wondering how you really get around expanding your like quantum startup and how you actually make sure everyone in the world gets like impacted to quantum computing.
Yeah. But please, for people that are really new to this field, please, as I said in my talk, don't think that it can happen. It will really happen. You should wait, and you can't really make money out of this now all over the world. Just I think you should decide logically and think about something that you can do beside the quantum computing, for example, data analytics, for example, programming, web development, something that just works for you, and you can just focus on your desired field like quantum computing, quantum information. Just not put your all focus on this, in my opinion.
Yeah. Thank you for that piece of advice. So I guess it's nearing 1 p.m. or 10 p.m. for Sarah. So does anyone has any last questions they'd like to ask? Okay, I guess that's the last few questions we have. Thank you so much, Sarah, for taking time today to speak with us. It was really valuable, and I think everyone learned a lot. We hope that you have a great success with your startup, and I wish you the best with it. Thank you so much for the amazing presentation, and thank you everyone for coming in today.
Thank you.
Thank
I really appreciate your invitation.
Of course, it was an amazing presentation. Glad to have you here. So this presentation will be recorded and uploaded to our community YouTube. Just type in Q-munity Tech on YouTube, and you should be able to find this video as well as our previous workshops that you can watch and learn more about quantum computing as well. So have a nice day, everyone, and thank you so much, Sarah, for presenting today. Have a nice day.
Thank you.
Yes. Bye. Bye-bye.